Good morning, everyone. My name is Kyungjin Oh from St. Paul Preparatory Seoul. Today, I'd like to share my project, Persistent Moisture Adjustment Regimes in ERA5 and Links to Extreme Events. Modern weather models like ERA5 combine short-term forecast with real observation from satellites and weather balloon. This process creates small corrections called moisture increments. These increments are usually thrown away as simple error fixes. What I wanted to know was, can these increments actually contain hidden patterns that tell us when extreme weather is happening? That's the core idea behind my project. I chose this topic because extreme storms, heavy rainfall, and flash floods are becoming more common because of climate change. If we can better understand what's happening in the atmosphere, we can help protect people and save resources. The main issue is that current models sometimes miss rapid changes in moisture that fuel severe storms. This is really important because these extreme events cause huge damage and affect many communities, especially in places like Western United States. This project directly supports United Nations Sustainable Development Goal 13, climate action. By improving how we diagnose extreme weathers, we can help societies better prepare for and adapt to climate change. My hypothesis was that ERA5 moisture increments shows consistent vertical patterns called regimes that are connected to extreme weather events. I used ERA5 data from 2019 to 2021 over Western United States, looking at specific humidity at 3 pressure level, along with K for instability and total precipitation. First, I calculated the moisture increments by subtracting the background forecast from the final analysis. Then I checked whether these increments were different from pure random noise using several statistical tests. After that, I turned each vertical columns of the atmosphere into 6 simple physical numbers, things like vertical coherence, magnitude, and energy changes. Next, I used 2 unsupervised machine learning methods, Gaussian mixture models and K-means, to automatically find repeating patterns in this column. Finally, I compared how often each pattern appeared during extreme CAPE and extreme precipitation events. The results were very clear. The increments are not random. They show strong vertical and time connections. Most of the time, the adjustments were small, but there is one special pattern we called R4. This R4 regime has large, vertically coherent moisture correction. It appears about 7 to 8 times more during extreme CAPE events and about twice as often during extreme precipitation events. Machine learning models confirm that R4 is the strongest indicator, especially for strong convective instability. In short, this moisture increment acts as a real-time diagnostic for organized extreme weather. So, my proposed solution is to start using this increment-derived regimes in reanalysis evaluation and day-to-day monitoring. We can turn data that is used to be thrown away into practical, low-cost tools for spotting extreme condition without needing expensive new instruments. The potential impact is very significant. This approach can help us better understand model weaknesses, improve extreme weather diagnostics, and support better disaster preparedness. It could even be applied in other fields like oceanography. In the future, I'd like to test this on longer time periods, expand it globally, and maybe combine it with real-time forecasting systems. Thank you so much for listening.